So good afternoon, everybody, and welcome to our 11th Quantum Portugal Initiative lecture. And today is our pleasure to have here Tim Taminiau from the Delft University. And thanks, Tim, for accepting to come today to our series of seminars. This has been a very exciting series till now, and with you here, I'm sure it's going to be is going to continue to be super exciting. So let me first introduce our speaker today. So Tim is a principal investigator in the quantum tech at Delft University of Technology, and his group that was established actually in 2015 is focused on solid-state defect spins, both at fundamental but also and technological applications on quantum information. So Tim graduated from the University of Twente in 2005, and then he obtained a PhD at TICFO in Barcelona. And then before returning to the Netherlands, Tim also was a stay in the US, first in Caltech, in the California Institute of Technology, and then in Brown University. And then he returned to the Netherlands, as I was saying, and he was actually awarded a ERC in 2015 as well, no? And also the Dutch Benny and BD career grants. So in 2015, he's also awarded the Fresnel Prize for fundamental contributions to quantum optics and electronics. So as you can see, he has a very strong background and very relevant pioneering work in the field of quantum technologies. And today, Tim is going to be talking to us about quantum network computation and simulations with spinning diamonds. And before passing the floor to him, I would like to remind you that you can place your questions in our questions and answers chat. And then at the end of the talk, I will pass you the word for you to ask your questions if you prefer. And with this, yes, again, a pleasure to introduce Tim, and please go ahead whenever you want. Thank you.
Okay, thanks. Good afternoon, everyone. I'm very excited to be here. It looks like an excellent series of seminars, and I'm happy to present some of the things that are going on in my group at QuTech at Delft University. So one of the main goals of my group is to realize quantum networks. These are systems where we have nodes that contain multiple quantum bits that can store and process quantum states. And in this case, these quantum bits are going to be spins in solids, and particularly spins in diamonds. And these little quantum processors containing a few quantum bits can then be connected together through photonic links, so using photons, using particles of light. Okay, why do we want to do that? The first motivation is that this is a way to realize large-scale quantum systems that we can use for quantum computation and simulation. So imagine that we can make these nodes, and we can make them good enough that they are suitable for quantum computation, and we can connect them together using these photonic links. Then, in principle, scaling to a very large system would just be a question of making many copies. All right? So such a network is kind of intrinsically modular, and that gives it an inherent scalability. That's one way to sidestep one of the big challenges, namely to create more and more quantum bits on one large chip of ever-increasing complexity. Okay, a second motivation is to use these systems for long-range quantum cryptography, or communication. So these photons can travel over long distances. So it's possible to make these links over long distances between cities, principal countries, and all over the world. And a final motivation here is always to see if we can get control over these kind of large, complex quantum systems and use these for fundamental tests of quantum mechanics. Essentially, test the laws of quantum mechanics in new settings where we haven't really been yet, and hope that perhaps at some point we'll find some surprises. Okay, and in this talk, I want to explain a bit about how these quantum networks can work, and in particularly how we can control many of these spins as quantum bits inside one of these nodes. So here's an outline. I'll start with a brief introduction to the main player in this story, namely the nitrogen vacancy center in Diamond, which is the defect that's the kind of the central access point to these spins. And then I want to show that we can use the electronic spin of one such an NV center to detect and control nuclear spins in its environment and use those as quantum bits. And then finally, I want to ask the question, how far can we kind of push that? Can we detect and very precisely control and characterize many of these nuclear spins as quantum bits in this way? And in particular, there we'll use the NV electron spin to detect and precisely image large clusters of many of these spins. And I'll show that we can get that up to about 27 in this talk. Okay, so first, an introduction to the nitrogen vacancy center in Diamond and how we use it as a quantum bit. So first thing you need is a diamond, perhaps obviously. And for this, we use diamonds that are grown in the lab with chemical vapor deposition. So here you see a CVD reactor in the clean room in Delft. If you look through one of the windows, and you see here a little diamond in a plasma, and we're growing on that seed diamond, we're growing layers of diamond to use in the experiments. So we can either do this ourselves in the lab or get these from industry collaborations, and particularly from a company called Element 6, that are the world experts on this kind of CVD processes for diamond. And then when we have a diamond, we look inside there for this nitrogen vacancy center defect. So this consists of a nitrogen atom that replaces one of the carbon atoms in the diamond lattice next to a vacancy, a missing carbon atom. And here some electrons are trapped together. They form an electronic spin system with spin 1. So there's 3 energy levels. Typically, we just pick then 2 of these and define a quantum bit, a 2-level system of that. Now, we perform our experiments typically at 4 Kelvin. So here you see a picture of a very old cryostat that was decommissioned, I think, 10 years ago. And what you see here is a little piece of diamond that's wired up on a PCB on a chip. We zoom in a little bit more. Here you see the diamond, it's a few millimeters large. And if we look with an electron microscope, then we see these kind of pictures. So this gray stuff here is just the diamond surface. And then we sculpture out these half spheres with solid immersion lenses using a focused ion beam. And this is just to get the light that is emitted by the defect, by the NV center, efficiently out of the diamond. Right? So diamond has a very large refractive index. So if we have a flat surface, we would get a lot of total internal reflection. But if we curve the surface everywhere, then the light efficiently exits the diamond. You can see down here in a fluorescence image where we just take a laser and we spatially scan it over this solid immersion lens. You see here the edge of that half sphere, and in the middle, one bright spot, which is one of these nitrogen vacancy centers that is fluorescing as we excite it with laser. We then also fabricate, for example, these microwave lines here, where you can send microwave pulses to, and those are then really to control the spin states of the system. So, for example, a very simple experiment is that we prepare the spin in, let's say, spin up. You apply a microwave pulse of varying lengths, and you rotate the spin from up to down to back up coherently. And here in the middle, for example, we have created a coherent superposition of spin up and spin down. You can see this can be done with very high quality, get a nice cosine, and also very fast. These operations, this can be done in about 10 nanoseconds or so. And I'll show you that coherence times for these spin systems can be in seconds or even longer. So that means that you get a qubit that you can control to very high precision using microwaves and detect optically. So how do we measure actually the spin state of this system? We use that using lasers, using optics. And this is how it works at low temperature, so it's 4 Kelvin. So we can park a laser on the nitrogen vacancy center, on the defect, and then we scan the frequency of that laser. And then you see that every time when we hit a transition from the ground state to the excited state, we see a sharp peak spike in fluorescence. And these different transitions, they are associated with different spin states. And I drew 2 of them here on the left. So this is, for example, a transition for the MSS 0 spin state, and here is a transition for the MSS plus and minus 1 spin state. So if we now want to detect a spin, what can we do? We can just turn on a laser that is resonant only with this transition for the MSS 0 spin state. So only when the defect in its the electronic spin is MSS 0, then we excite the system to the excited state, and it fluoresces, and we detect light. If we're in the other spin state, then in principle it stays dark and we don't see any light. So that gives you a very high quality, high contrast readout mechanism for the spin, where you can really in a single shot determine the spin state with up to about 98% fidelity. So 98% probability to get the right answer. And here you can see how it works, right? So if we prepare the spin state up, it's MSS 0, we turn on this laser, we create fluorescence, and we detect on average about 8.5 photons. Whereas if we prepare one of the other spin states, it stays dark and we detect on average about 0 photons. Now this readout mechanism is not perfect, and that's because here in the excited state, there's some probability for processes to happen that flip the spin, and then we cannot collect any more photons. Right? So the game here is really to be able to detect at least 1 photon before the spin flips. And that's why these solid immersion lenses are so important here, because they increase the collection efficiency by about a factor of 10. Okay, so that gives us ways to control the spin and to measure it. So what else makes this system so interesting? And really one exciting property here is that this spin system is extremely well isolated from the environment. So you can see that, for example, in this experiment, this is a so-called T1 experiment, or electron spin relaxation. So here we prepare the spin just in one of its eigenstates, one of the 3 eigenstates. And then we wait some time and we measure, is the spin still in the same state? So up here, the spin is preserved. And then you see that even after waiting a long time, for about 10 minutes, there's hardly any decrease of the signal. So if we prepare the spin in one of its states, it stays there for at least 10 minutes, and we can fit a 1/e time of about 1 hour to this. And we actually also know that this little decay doesn't come from the actual qubit relaxing, the spin relaxing, but it comes from our lasers and our setups drifting over time on time scales of tens of minutes. So this means that this spin system is really well isolated from its environment. There's nothing like, at least in the ground state, there's nothing like spontaneous emission or any interaction with phonons, like vibrations of the diamonds, to worry about. And that means that we can hope to really control and understand these systems to a very high precision. And an example of that is if now we look at the electron spin coherence. So where you make superposition states of the electron spin and see how these evolve and how they dephase or decohere. So the coherence of the electronic spin is typically limited by nuclear spins in the environment. So naturally, the diamond consists of about 1.1 carbon-13, which also carries spin, it's a spin half. The rest is carbon-12 and it has no spin. So that means that around this NV center, there's always this carbon-13 nuclear spins that are randomly positioned. And if you don't control them, they move around and they flip-flop with each other, and they create a noisy magnetic field on the NV center. So if I do an experiment where I create a superposition on the NV electron spin and I let it evolve, it feels some magnetic field from the environment. Sometimes later, that magnetic field will have changed, became a bit weaker in this case. And because that magnetic field fluctuates, the electron spin in its Lamour procession picks up different phases. Those average out, and in the end, we lose the spin state, or the phase becomes undetermined. It dephases. So you see such an experiment where we just apply a pi/2 rotation that just creates a superposition on the electron spin. We let it evolve over time, and you see the quantum state decoheres or dephases in about 5 microseconds or so. So that's not yet a very long coherence time. And what can we do about this? So we can protect this electronic spin from this nuclear spin environment using a trick called spin echo or dynamical decoupling. So now in the middle of this kind of sequence, we are going to apply a pi pulse, which just inverts the spin. And by inverting the electronic spin, we also invert effectively its interaction with the environment. And that means that if the interaction with the environment, this magnetic field, is stable over time, then if I have the same time before and after that inversion, it will exactly cancel itself. So independently of what the magnetic field is at that moment in time, it will cancel itself. Now that only works if the magnetic field is completely constant. But if it fluctuates slowly by just flipping the electron spin fairly rapidly, we can average out any interaction. That's what you can see in this data here. So here we create a superposition on the electronic spin. Up here it's preserved, stays coherent. And down here it is lost, dephased. And you can see that as a function of the number of times we flip it, and the number of pi pulses, starting here at 4 and then here to the right all the way to about 10,000, we can protect the electron spin longer and longer and longer. And this is on a log scale. And over here with about 10,000 pulses, the coherence time becomes about 1.5 seconds. So you can really decouple the electron spin from its environment and extend its coherence, and in this case by about 6 orders of magnitude. So that works very well. In this way, we can create a very coherent system where we turn off these interactions. Okay, then one question is, like, how do you then make bigger systems? How do you get more quantum bits in your system, or how do we build these networks? And there we can make optical links between these NV centers over a distance. I'm just going to briefly sketch how that works. We'll not go into all the details, but just to give you some idea how this can be done. So we take 2 NV centers in 2 different diamonds. They're from distance away from each other. And then what we do is on both sides, we create an entangled state between the spin and the photon. And in this example, we can do this by hitting the spin with 2 laser pulses. And if the first laser pulse is resonant with the MSE0 state, then we create 1 photon with that first laser pulse. And if the second laser pulse is resonant with the spin 1 state, then we create a single photon in that second laser pulse. And they're called here early and late. So we get an entangled state between the spin and the time at which a photon was created. And we do it on both sides, and then we interfere these 2 photons on a beam splitter. And after that, we can fundamentally not know anymore which photon came from which NV center. And that means if we now perform a measurement of these photons, and we get a certain pattern of clicks, we detect these photons in some state, then we, for example, know that one NV center is pointing up and the other NV center is pointing down, but we don't know which is which means that we project the system in an entangled state like this, right? Where down up with some phase relation to the state up down. So in this way we can establish entangled states over a distance between these NV centers without any direct interaction between them. Now, one thing that's important to realize here is that this is, of course, kind of probabilistic. It doesn't always work, both fundamentally and due to the, how these beam splitter and detectors work, but also because photons tend to get lost on the way. But what is very important here is that you can just try this until you succeed. And when you succeed, you get this click pattern. In this case, both detectors click. And then it's heralded that now you have generated this entangled state. So you know you have it, and then you can deterministically or efficiently use it to perform all sorts of network operations. Okay, and this works. One of the prominent examples of that is this experiment that we did some time ago now, where we entangled two NV centers over a distance of about 1.3 kilometers. One NV center being a diamond in the physics building here in Delft. This is where I'm sitting right now. And the other NV center being in our nuclear reactor institute on the other side of the campus. And this beam splitter and detectors are here in the electrical engineering building that is about halfway. And with that, we could show that we could create entanglement even over such large distances of more than a kilometer. In this particular case, we use this to perform something called a loophole-free bell test. This is an experiment to kind of pitch your local locality of classical physics towards the inherent non-locality in quantum mechanics. I won't go into the details. The outcome was quantum mechanics is still right. But I just want to show this in the sense that as a take-home message here is that we can make these optical links, and this works well. Then the group of Ronald Hansson, colleague of mine here at QuTech, that also was in leading this bell test experiment, already went further than that and also started entangling multiple nodes together. So for example, here, 3 of these nodes together, by first making entanglement between these two, called Charlie and Bob, then storing that entangled state in one of these nuclear spins as an extra qubit, and then also making entanglement between Alice and Bob here, and then fusing everything together to be able to create larger networks. And that's important because if we want in the end to build large networks, this is probably the way we have to do it, where we have these additional qubits in the nodes to store and process these quantum states. You have this additional memory and computation power in the nodes. So we need to have more qubits there. And that's what I want to talk about next. Like, how can we create control of multiple of these spins or inside one of these nodes for these networks? So we're going to look into how we can use the electron spin to detect and control nuclear spins in the environment. And so the key idea here is that the electron spin is not alone. It's surrounded by all these nuclear spins. And I've told you by just flipping the electron spin around, we can decouple it from those nuclear spins. But now I'll show you that by flipping the electron spin around with a precise timing, we can actually decouple it from all the nuclear spins, but selectively couple it and control individual nuclear spins in the environment. And then, for example, by flipping the electron spin with a different frequency, we can control other nuclear spins. Okay, how does it work? So I showed that if we flip the spin, we invert the interaction, and so if the interaction is kind of like static, then it cancels out. But what now if this magnetic field that is being generated by a nuclear spin actually is not static, but it oscillates, and it oscillates in a frequency that's exactly commensurate with the pulses that we do. Right? So now we don't average out the interaction. Instead, every time the interaction inverts, we also invert the spin. So we actually rectify the signal. So if we apply such a train of pulses, we actually become sensitive to dynamics, to interactions with specific frequencies. Okay, so we can use that to probe the environment. So this is the same type of experiment. We create a superposition of the electronic spin state. And up here it's preserved. And we apply 32 of these inversion pulses, but now we sweep the time between the pulses. So they're the spacing between the pulses. And up here is like where the electron spin is preserved. And before I was showing you just points that we selected here where you can protect the electron spin well. But now you see there's all this additional structure. And I want to focus particularly on this kind of sharp features, let's say here. You see they all, there's a lot of dips in the coherence signal. The electron suddenly loses its coherence. If we zoom in a bit more there, we see these sharp dips appearing. For example, this blue one here, and it repeats in time. So this is now really the electronic spin sensing and getting entangled with one nuclear spin in the environment. You also see this kind of like more broad feature here. And that is really the electron spin entangling with many spins at the same time in the environment. There's a big mess, and that we call decoherence. But in these kind of sharp features, we're talking about individual spins. Okay. In this case, it was easy to detect about 7 spins out of this data by analyzing this. And so this is how we can use the electronic spin as a kind of sensor for its environment. Now we want to also control these spins as qubits. So this picture I sketched is a bit classical. Now I want to look at what actually happens on a quantum level to these spins. And the key idea here is really that the nuclear spin evolution depends on the electron spin state. So imagine I have a nuclear spin, just a 2-level system, and spin half, and I apply some magnetic field in the z direction. So if I now wait, the nuclear spin just will precess with Lamour precession around that axis, the z-axis defined by the magnetic field. And that's true for all these nuclear spins in the environment. So this is that only holds if the electron spin is in the MSS0 state. It's like the electron spin is not there. However, if I now flip the electronic spin, for example, to its MSS-1 state, it creates this small dipolar magnetic field. And that slightly changes the precession of this nuclear spin. It both changes its frequency, the strength of the field, but it also tilts the field a tiny bit. So by flipping the electron spin around, I can choose the axis around which the nuclear spin processes. And now maybe you can imagine that if I have 2 rotation axes in 3-dimensional space, and I switch between those, then I can rotate anywhere in 3-dimensional space. So I get universal or complete control over that spin state. And maybe you can also imagine that 2 rotation axes that are not parallel, these do not commute. Right? The order of rotations matter. And that means that you can also do what we call controlled quantum gates, or 2-qubit gates, essentially operations that make entanglement. And depending on what state the electron starts in, the nuclear spin will undergo a different evolution. And finally, because each of these nuclear spins has a different location relative to the electron spin, it feels a different magnetic field. And that means that we can also selectively control them. Okay, the math behind this is a little bit more complicated, but these are the principles. So we can just apply this train of pi pulses. And then we generate an interaction like this. So this is in a circuit level, circuit diagram language. So we have a controlled rotation of the nuclear spin that's controlled by the state of the electron spin. The interaction you then generate is this kind of SZIX kind of interaction in the Hamiltonian. It just means that the electron spin picks up a phase depending on the X projection of the nuclear spin. And that's how we can sense them, right? The electron spin picks up a phase depending on the state of the nuclear spin. But you can also think of it as the nuclear spin undergoing some X rotation or Rabi oscillation, depending on the state of the electron spin. Okay, so that gives us a mechanism to detect and also control these nuclear spins. Now, these nuclear spins are also very interesting qubits by themselves. A particular feature they have is that they have very long coherence times. So here you see a similar experiment where we apply these echo pulses, but now on the nuclear spin state. So we bring it into a superposition, apply up to about 256 pulses, and then you see that the coherence time here is in the order of a minute. Yeah, so these nuclear spins can really hold quantum states and protect them on kind of human timescales. Very well isolated quantum bits. Okay, I want to brief side tour. What else can you detect in the environment? Right? So we said we have this NV center. We can use it to detect and control these nuclear spins in the environment. What else is out there? And it turns out that there's much more things in the diamonds that you can detect and you can play around with. So one thing that happens is that you can also have two nuclear spins that are right next to each other in the lattice. And then these nuclear spins feel each other very strongly. And they essentially create a new type of atom, right? Their Hamiltonian or their energy levels are strongly modified by the fact that they're coupled together because they're right next to each other or very close to each other. They form a pair, and that's kind of a new system. It has its own unique frequencies, so we can also detect those. And then we have shown, for example, in this paper that we can detect multiple of such pairs, control them as quantum bits, do gates, entangle them, and etc. And one cool property of these coupled spin pairs is that they form kind of atomic clock states that make them really, really long-lived. And their dephasing time, T2 star, is up to about 2 minutes. So those are very robust quantum systems. You can also try to look out further in space, and at some point then you find other defects. For example, these kind of P1 centers, which are just a nitrogen atom in the diamond with essentially an NV center without the vacancy. And those have also an electronic spin, and we can also detect and control again these as individual qubits. If you want to know more about that, you can look into this paper. But here I want to say a bit more about how can we control many of these nuclear spins and characterize them precisely. So the first step there is really like, okay, how can we characterize that environment, essentially image them, right? One way of saying what we want to know is we want to know where each of these nuclear spins are so that we understand very well how everything couples together. So how to characterize this quantum processor? You can also think about this, how to, in other words, or another motivation, how to realize atomic scale magnetic resonance imaging. Right? So use the magnetic fields from these spins to image them, but really with single spin and atomic resolution. So we're going to take the NV center, use it as a sensor, and then try to image a large cluster of these nuclear spins in its surrounding. And the method that we're going to use is that we're going to try to measure the nuclear interactions, so the interactions between the nuclear spins, because those really reveal the composition, how many nuclear spins are there, and how they are connected in this cluster. And that we can then transform back in these measured couplings into the three-dimensional structure. Okay, so one motivation is this is our quantum processor. We want to analyze it and to understand it. The second motivation that I mentioned is to do atomic scale magnetic resonance imaging. And here you can think about the following as a kind of longer-term vision. Imagine we can now take interesting systems, maybe proteins that play a role in medicine or biology, place those on top of the diamond, have a defect center close to the surface, and now use it to image on a level of individual atoms such molecules. Okay, that's very challenging because you get all the kind of like surface chemistry and everything comes into play. But there are many beautiful theoretical proposals out there of how we could do this. What I want to show you now is an experiment that shows a method that could be used also for imaging such systems outside of the diamonds. But we're going to do it on the nuclear spins that are inside the diamond. Okay, so let's start at the beginning. What we're going to do is we're going to take one of these nuclear spins, put it in a superposition, and let it process. Okay, we do that with this sequence here. Don't worry about the details, but we apply one of these trains of pulses in order to first detect what is the nuclear spin state. Then we let it evolve, and then we detect again how it has evolved. So this is called a Ramsey experiment. And here you see it in the time domain. So here we create a superposition state on a nuclear spin, we let it evolve, precess. And you see it, its magnetization oscillates in some sort of complex way. Right? An oscillating signal, but also with some beating some envelope. So that already means that this spin is feeling some sort of complex environment, and depending on the state of that environment, it evolves with different frequencies. So we can Fourier transform this, okay, get some really complex spectrum, don't really know what to make out of this. And the reason for that is that we have underlying here is a lot of information. So for the cluster that I will show you, there's about 50 million spectral lines in this spectrum. And our spectral resolution is just not good enough to resolve anything here. And ultimately that comes down to the nuclear spin dephasing over time. The signal shrinks. And in the time domain, and that translates to the spectral resolution of the measurement. So we can't tell small frequency shifts apart because we just don't have enough coherence. Okay, so what's the solution? We're going to do these kind of echoes again. So now we apply a train of pi pulses on this nuclear spin and decouple it from its environment. Okay, and that's what you see down here. So again, up here the coherence is preserved, and if we apply multiple pulses on this nuclear spin, we can protect its coherence, in this case to about 10 seconds. Now the spin can evolve for a long time, and even a very small field, very small coupling that would change the frequency slightly would be detectable. However, we have absolutely completely decoupled the nuclear spin from its environment. So we lost all the information of what is in its environment. So we play one more trick, and we apply another train of pulses that now will also flip this spin over here. And we're going to flip these two in unison. So we're going to flip them together. This is called spin echo double resonance in nuclear magnetic resonance, NMR. So now we protect these two spins from their environment, but we maintain the coupling between them. Okay, so now if we look in the time domain signal for spin number 1, we see an oscillating signal, which just encodes the coupling to spin number 2. We can Fourier transform that, and we see two peaks. One peak is the frequency of spin 1 if spin 2 is up, and the other one is the frequency of spin 1 if spin 2 is down. And what you can see now is that we can detect these with very high precision. So the line width here is really in about 80 millihertz or so, and the coupling between these two spins is only half a hertz, and we can really get that with a microhertz kind of precision. Yeah, so that gives us now a method to detect the interactions between these nuclear spins very precisely. And then we just turn this into a big data set by kind of sweeping all the parameters. So here you can see that we fix this first frequency, we sweep the second frequency in this direction, and every time you see a peak, that means that there is a nuclear spin in the environment at that frequency that also couples to our first nuclear spin. If we change the time in this dimension, then we learn something about the strength of the coupling. And then finally, we can also sweep that first frequency to kind of create a three-dimensional data set that now really encodes the composition and the connectivity of the whole thing. Now, this problem becomes very overdetermined because there's order 3m coordinates. Every spin has 3 coordinates, x, y, and z in space, but the number of couplings or interactions grows exponentially, grows quadratically, right? Goes as m squared. That means we can, in principle, invert this problem. Okay, we then wrote computer programs to do this. One thing to consider there is like, how do you discretize your space to be able to kind of turn this problem into a fitting problem and resolve it? You can do this in 2 ways. One, you can use the a priori knowledge that all these nuclear spins are on a diamond lattice. Right, so you know that they are on the lattice of diamond. That makes your life enormously easier. But we also did it without taking any a priori knowledge into account and just discretizing space in some sort of fine cubic mesh. And in both cases, we find the same result. Although that is much more computationally heavy. But of course, if you would want to apply this in the end to proteins outside of the diamond, then you cannot assume them to be on the atoms to be on a nice lattice. Okay, here you see the result of that analysis then. This is essentially just a coupling matrix or kind of a two-dimensional spectroscopy of the interactions between all these spins. So one of these dots just means that there is a spin at a frequency of about 480, and it couples to a spin at about that has a frequency of about 460, and the color and the size of this dot then tell you how strong the interaction is. And the computer program then returns to us that we're looking at 27 nuclear spins in our data. And here you see their spatial coordinates. So this is then, for these 27 spins, how they're positioned in space. You see the whole thing is pretty small, right? It's maybe 3 by 3 by 3 nanometers or so. We can do some least square fitting to get some idea of how sharp these the minima are and get some idea of the errors. And you can see that that any uncertainties on the 77 spatial coordinates of this system are well below the bond length of diamond and deep sub-angstrom typically. Right, so we really get kind of atomic resolution of where all these spins are. Okay, now you might ask, but where is that NV center then? Right, it's not in this picture. Of course, if you just want to image this system, you don't really care, but we want to use it as a quantum processor. We actually also want to understand where the NV center is and how it interacts with the with all the spins. So what we do there is then we use the nitrogen nuclear spin of the NV center and also couple it to all these carbon spins in the environment. Well, actually 12 of them, and do the same trick. And that allows you to also position, find the position of the nitrogen vacancy center. So the green dot here is the nitrogen atom next to the missing carbon atom in the lattice. To give you some idea of what this looks like, a little bit better. Here's a three-dimensional. Oops. Here's a three-dimensional video of the of this cluster. So the white balls here are the carbon 12 atoms. We don't care about them; they're spinless. The yellow ones are these 27 carbon 13 atoms that we're characterizing and using as our want to use as our quantum bits. And then here in the middle is the nitrogen. And the vacancy of the NV center. So we use that electronic spin here to couple and to control and detect all these nuclear spins in the environment. The hand down here shows that this is not a video, but like a model using this kind of like chemical stick and balls that the students built in to put in the lab. I think that took them an entire day to do. It was a kind of a hard job. Here you see them working on them. This over here is Mohammed Ababai, was the leading PhD student on this imaging project. Okay, why are we excited about this? 3 reasons. First, we think this is an interesting system for quantum simulations. Second, it is a quantum processor that we can use for exploring quantum computation. And finally, these can be our nodes for quantum networks by combining them with these optical links. And I just want to say briefly, still have some time, a few things about kind of what the state of the art is or what's going on there in these topics. So first, why is this interesting already at this stage for quantum simulations? Well, we now have this kind of like large interacting spin systems that are really well isolated from their environment. So they're described by some sort of simple physics, dipole or spin-spin interactions. But because the system is large, it starts to become very difficult to calculate. So this becomes kind of a natural simulator for quantum many-body spin physics or problems in condensed matter physics. One example that I briefly want to say something about is that we have kind of the first problem we try to crack with this simulator is to realize something called a discrete time crystal. So what we do here is we now took 9 of these spins that are positioned so in space that they form effectively a one-dimensional chain. And their interaction Hamiltonian looks one-dimensional. where they couple mostly to their nearest neighbors, and then the coupling falls off rapidly. So that's a chain of spins, and one thing that has been predicted to happen there is that if you have an interacting chain of spins or qubits with some strong disorder on these interactions, then you can realize something called a discrete time crystal. So this is kind of like a new, predicted many-body phase of matter, where you take all these spins and you periodically flip them around, and they form a stable phase of matter, in the sense that even if you now perturb the parameters of the system, or these flips are imperfect, all the spins synchronize up, and they show a stable oscillation. This is called a time crystal, in analogy to how a normal crystal, if you have a piece of diamond, right, in space itself has translational symmetry, but if you put a bunch of atoms together that interact, they form a crystal that has now a periodic kind of symmetry. So this breaks the translational symmetry of space, and similarly here, this system breaks the discrete translational symmetry of its own Hamiltonian. Yeah, so that's something that we could demonstrate using this system. So the details you can find in this paper down here. What I really want to show with that is that yeah, this kind of coupled spin systems, where you have really individual control over all the spins, and you can control their interactions, allows you to study interesting problems in many-body and condensed matter physics. Okay, second, you can also think of this as a quantum processor. So here are two other recent results from our group. First, where we then used 10 of these spins as kind of like a demonstration 10-qubit quantum processor. And then one thing that we showed here is that we could connect all the qubits together. So create entangled states between any of the qubits pairwise. And here we create all possible 45 2-qubit Bell states in the system. So that shows that the processor is kind of fully connected. We then also use the same type of system to look into doing fault-tolerant operations on logical qubits. Okay, that maybe needs a little bit of unpacking. So in the end, if we want to build large-scale quantum computers, then we need to encode logical qubits, so logical one qubit of logical information spread out over entangled states of multiple physical qubits or spins. And do this in such a way that we can operate on the system so that small imperfections actually can be overcome. So you can do reliable large-scale quantum computation, even though the underlying components themselves are faulty. Okay. So here we show the first step towards that, where we encode such a logical qubit over an entangled state of 5 of these spins, and then perform operations like gates and measurements, and that can help you, that can detect errors in such a way that if one of the operations fails, the system is robust against that. It's fault tolerant. Right? So a single error happening somewhere doesn't actually break the information. Okay, that's just the first kind of exciting step towards what we need to do to, in the end, get to large-scale quantum computation. Okay, and finally, yeah, the real end game here is to bring all these things together and to have nodes that contain many qubits that we can control to very high precision, and then also link these together using photonic entanglement links, and in that way move towards large-scale networks for quantum communication, quantum cryptography, and tests of quantum mechanics. Okay, with that, I would like to thank you, and I'll leave you with a photo of the people from the group. Thank you.
Thanks, Tim, for this very inspiring talk. Indeed, very impressive, results. Okay, so then I will open then the lecture for questions, and I cannot see any specific question here in the Q&A from any student, but we have some questions from Ernesto first. I also have some. So maybe I will open the mic for Ernesto to ask the questions himself.
Okay, can you hear me?
Yep. Mm-hmm.
Good. Okay. So thanks a lot. It was a wonderful talk. I had no idea this spin manipulation with NV centers was so advanced. So one question is regarding this 3D spectroscopy technique that you described. So you mentioned that you could map 27 spin qubits around the NV center. So what sets the horizon there? Like if you improve the methods, can you increase the voxel that you're interacting with? And the related question is, can you try to use maybe two different NV centers coupled to the same set of spins to improve the control techniques? Is that something you're thinking about? So two questions, sorry. Yeah.
Yeah, let me try to answer these two questions. Let me maybe first draw up some picture. This one. Yeah, so what sets this 27 spins that we detected here? So the first thing to realize there is that the space that we selected to image here, we really select this in frequency space, right? So we limited ourselves to a certain frequency space, and that contains this, that maps onto this spatial distribution. So the first limitation there was that it just takes quite some time to do this. And this experiment took 400 hours. So we stopped at that point. You can push this further out, for sure, somewhat further. But at some point you run into challenges due to spectral crowding or overlap. Right. So in this case, the only reason why these nuclear spins are unique, why they have some unique frequency component, is because they couple to this electronic spin of the NV. And the farther we go out, think about a shell around the NV center, the farther you go out, the number of spins in that shell increases with r to the power 3, and the coupling to the NV center goes down with r to the power 3. Right? So spins start to become more and more identical the farther you go out. And so you essentially end up with some sort of spectral crowding. In principle, you can do echoes and so, and you can do a lot of tricks, but practically there will be some end to this. And to give you some idea, I hope to push this at least to 50 and maybe to 100. Then it's probably going to be tricky. And then having two NV centers, for example, yeah, I think this is an interesting idea. To use multiple NV centers to detect the same nuclear spins. A challenge there is at least that in the concentration we use now, this system is only 3 by 3 nanometers large or so. And the next NV center would typically be 10 to 20 nanometers away. It's difficult to get them so close to each other. One particular challenge there is that I think below 5 nanometers or so distance between the NV centers, they will start to interact in the sense that the charges might jump back and forth and so on. It's not really, at some point it's not an NV center anymore, it becomes like a 2 nitrogen, 2 vacancy defect. So there are some challenges there, but I think it is possible, and there are certainly proposals out there to use multiple NV centers to look at nuclear spins in, let's say, molecules farther out there and to be able to image them with multiple NV centers.
Thanks a lot.
Thanks, Tim. Yeah, we had a question by Miguel Ferreira Cao, but it seems that you have already actually answered it during your reply to Ernesto. But in any case, I think he was asking about the spatial resolution of your measurements in the 2D and 3D spectroscopy, and I'm not sure if you really answered that. Could you comment on that as well, on the actual spatial resolution rather than the number of bits that you can expand? No? Yeah.
So in the end, this is a kind of like NMR or MRI-like technique, right? So we try to get a very high frequency resolution, and then we turn that into a high spatial resolution. And the frequency resolution is extremely good here. Then we have to invert this into space, right? And there one faces let's see. So in principle, that gives you also very high spatial resolution, right? So here you can see the uncertainties on these spins relative to the coordinates of the first one, and you see that all 77 coordinates of the system right, are below a diamond bond length, and in many cases here we're quite sub-angstrom. So we really think we know the positions of these spins with like sub-angstrom resolution.
Okay.
Of course, this is a little bit tricky, right? Because there is an underlying model that we need to use to invert from frequency to space. And we are taking into account here all sorts of like second order contributions to the Hamiltonian because of the kind of like electron spin modifying the nuclear spin interactions, and we're canceling those out with some additional techniques. But it's probably also quite difficult to be 100% sure what exactly would be your spatial resolution. It is at least quite high, like sub bond lengths. Yeah.
Okay. Yeah, and I actually have also a curiosity there with the coupling. When you mentioned, well, before starting to talk about many the 27 spin cluster, no? You mentioned that for the coupling of just two nuclei, that the coherence time gets longer actually with the coupling. I was expecting it the other way around. So did I get it wrong, or could you mention why is that? I saw you have an archive paper posted there on that.
So I'm not sure if I understand the question.
So you mentioned, I think I understood that you mentioned that upon coupling, no, between the nuclei, the coherence time of the couple system gets longer than the individual spins. Yeah. Is that correct?
You mean for this time crystal?
Yeah.
Yes, it's not so much the coherence time, but it's the specific response of all the spins synchronized, flipping their spin in time, right? And yes, if you have no interactions, then that immediately, very rapidly, each spin does its own thing, and they all decohere very rapidly. And it's due to the interactions that stabilizes this system. Yes, due to this kind of many body interactions in the system, and in particularly also due to the disorder in these systems. So ultimately, this is a version of a kind of like many body localization, which may be something that you've heard before, right? So this is a kind of many. They get synchronized to their interactions, and become stable due to their interactions, and then many body localization kind of stops the system from being able to absorb energy or heating up or thermalizing. So at least in theory, it can last forever, right? And then that's the interest of this time crystals.
That's right. Okay, so and we have another question by Jana actually. So I'm gonna pass her the floor now.
Hello, first of all, I would like to thank Tim for the excellent presentation and for accepting the invitation to join the QPI lecture series. Excellent talk. I believe ours a lot on various quantum processes, from coherence atomic clocks to quantum sensing, quantum processes. So my questions would be more on on your vision in these application areas that you quickly touched, where you mentioned the vision, for example, to perform atomic scale magnetic resonance imaging on molecules. Like, how far do you think are we from, like, what are the simplest molecular system you could imagine of measuring? And the second question would be related to the possibility that you discussed in the later part of the talk on the quantum processor, how the NV center-based quantum processor would compare to, let's say, the superconducting qubits based processors. If you could just like give some evaluation of that from your perspective. Thanks.
So maybe first this imaging of atomic scale magnetic resonance imaging of in the future single molecules. I mean, this is very challenging because interesting molecules, like let's say proteins, are very complex, right? And they also tend to be more difficult to handle. So there's several challenges there, like bringing the defect centers close to the surface reduces their coherence due to surface defects, dangling bonds, and so. It's difficult then, of course, to get a good system on top of that, all in a controlled way. But if you can do that, then in principle, I think these kind of methods can be used. People have done already things like electromagnetic resonance, right? So EPR on individual proteins using near surface NV centers and so. As well as NMR on really nanoscale kind of volumes of liquid. But yeah, this will be one step further where you also really get some sort of atomic resolution on the system. It would, as you can see maybe from my talk, it would require you to manipulate the system that you're looking at also quite precisely.
Yes, yes.
But yeah, I think we'll go that direction, and then,
yeah.
But I don't think it will be super soon.
Thank you. Yeah, I imagine. Mm-hmm.
Yeah, and then maybe a word about kind of like quantum computation side of things, right? So I would say first, in a very general comparison, like the reason why we are excited about this type of system, like these optically active defect spins, is that it combines two things, right? Like so very good qubits with these optical connections so you can build networks. And that gives you kind of an inherent scalability to the problem, in that if you can make modules that are good enough, one can just start making copies, right? So that is an important comparison to some systems that might not have optical connections or not have long-range connections. Another important advantage is the operation temperature, right? So for NV centers, it's about up to 10 Kelvin. I also work on other defects in other materials, silicon carbide. There's about 20 Kelvin. That is can be a big, potentially decisive advantage in the future compared to systems that require millikelvin temperatures. So that's some zoomed out arguments of why this system is interesting to look at for computation. If you look a bit more at the state of the art, at the moment it's quite competitive with other systems. So here we're looking at this fault tolerant operation of a logical qubit and perform kind of like stabilizer measurements non-destructively, in real time process the error syndrome information and perform corrections. So this is something that, for example, with superconducting qubits has not yet been shown. I'm pretty sure that Google and IBM will manage to do this at some point, perhaps in the near future, but it's something that is still missing for superconducting qubits. There are two really fantastic papers with ion traps that also that have already managed that about half a year before us, or a year before, for one of these papers. Right. So yeah, all these platforms are kind of like developing together, and there's some long-term pros and cons. But currently there's still quite some competitiveness there, and I think it will be exciting to see where it goes.
Thank you very much for your feedback. Very interesting. Thanks.
Okay. Yeah.
Okay. So I think we don't have any other questions. So then in that case, if no one else have a question, then I would like to thank you again, Tim, for this very nice talk and for being here for our 11th lecture. It was really nice to host you. And yeah, you are welcome to come physically anytime to INL, of course, to visit us.
Yeah, I'll be happy to do that.
Yeah, let's hope things are getting better, no? Hopefully soon. Okay, so yeah, and with this, I would like to thank also everybody who attended the lecture today, and well, and we will see each other in our next series then. So goodbye, everybody.
Okay, thank you.